Z-axis data acquisition refers to depth information derived from images, which is one aspect of the science of photogrammetry, a word coined by Albrecht Meidenbauer around 1915, meaning drawn to measure by light, or measuring things via images. While a single image may suffice to derive quite a bit of spatial information about a scene, multiple images are much preferred. Our eyes are capable of providing enough information about a scene before us that our brain can construct a three-dimensional model of the scene. For the explanation of this phenomena, we have to thank Sir Charles Wheatstone, who first explained stereopsis in 1838. As this occurred before the advent of photography, he was obliged to hand-draw his stereo pair illustrations, which were then viewed via this device, a mirror stereoscope. Drafting his illustrations meant that the images were necessarily spatially dimensioned in order to achieve the desired stereopsis. Thus, in a sense, photogrammetry actually preceded photography, an astounding concept to come to terms with. So what we learn from all this is that for most Z-axis data acquisition systems, multiple images are a prerequisite. In some cases, these are sequential, as with topographical mapping cameras, as well as motion picture footage in which the camera and/or the subject moves. In others, and especially for motion capture applications, multiple cameras are employed, which result in both sequential and simultaneous image acquisition. For such systems, at least two, and preferably more than two images, are required for adequate data acquisition. 4 images are a requirement of some systems, and it can be readily appreciated that this implies a substantial increase in the complexity and expense of cinematography. While motion picture production generally implies a 35mm film camera, it is of course possible to use video cameras, especially if they are high def. Or a possible combination would be a film camera with supplemental images acquired on several video cameras, which need not be high def. But any such system can't fail to add complexity and expense and incur increased time in the operation of the additional cameras and the management of the additional recording media, whatever it may be. In the post-production phase, the logistics of keeping track of numerous original neg and/or videotapes can be daunting. It is the object of the present paper to describe one possible alternative to the multiple camera approach, a monocular approach to Z-axis data acquisition. Now, when we say monocular, we do not actually mean mono-image. The monocular refers to the fact that we employ a single lens on a single camera. However, our single camera is able to acquire multiple images of the subject simultaneously. To achieve this, we start with a 35mm motion picture camera, renowned for its superior imaging capacity and well established as a workhorse of visual effects, the VistaVision camera. This one happens to be the Trumbullflex, a high-speed VistaVision camera designed by Academy Award winner Don Trumbull at Apogee Productions. Many of us have long understood that this venerable effects camera format had its beginnings back in the mid-1950s at Paramount. And that was certainly the understanding that I had as a student at the London School of Film Technique in 1956, when VistaVision was being trumpeted as a great innovation for the film White Christmas. In fact, it's quite a bit older. The first 8-perf camera was produced in 1918 by the Italian inventor and cinema pioneer Professor Filoteo Alberini, who in turn based his camera on the still camera designed by Oscar Banach of Leitz in 1913, which eventually became the famous Leica camera in 1924. And this is the first known 8-perf image made by Banach in 1913. A VistaVision camera, of course, achieves much of its performance by virtue of the substantially larger image area when compared to conventional 35mm 4-perf camera. The dominant aspect ratio for conventional 35mm production currently is 1:85:1. And here is what a 1:85:1 frame looks like on a piece of 35mm film from a conventional 4-perf camera. This provides an image area of 368 thousandths of an inch. By contrast, here's a VistaVision frame which at full aperture provides an astounding 1.5 inches, which is 4 times our conventional 185:1 image area. But let's take our normal 185:1 frame and place it in the middle of the VistaVision frame. All right then, now here's a Super 16 frame. This format has often been used as an economical alternative to 35mm production. The 144 thousandths image is blown up optically for 35mm release, and the results are generally quite good. So, if we take this Super 16 image and place it on our VistaVision frame with the 185:1 image in the center, we can see that it fits quite nicely in the corner. Indeed, we can fit each corner with a Super 16 frame. All very well and good, but how then are we to provide images to all these positions in the frame? Well, the answer, of course, is that it's all done with that staple of the visual effects trade, mirrors. Borrowing shamelessly from Sir Charles Wheatstone, we provide our VistaVision camera with a variety of mirror arrangements, such as this breadboard version. Being off-axis, they can provide the information we need to generate a three-dimensional model. Here's a schematic view showing the image paths. So let's take a look at what we have recorded with this arrangement. Here we have the VistaVision frame in the center. We see the view direct from the camera lens of the subject, and around it we see the images acquired from the mirrors. Because we have employed 2 mirrors for each image, we have inverted the images back to normal. Had we only reflected off of one mirror, we would have inverted the images. Not that it matters a great deal. The VistaVision frame is then digitally scanned, and here we will immediately appreciate another advantage of the system. We're only going to incur the standard rate for such a scan. We may have a dozen images in our frame, but we're only going to be charged for one. Later in software, we'll separate out the multiple images and create the various files. But here, they're all neatly bound to each other in one coherent package, a file management dream. You'll notice that there's a difference in size and appearance of the supplemental images. This is because we've employed mirrors with a convex curve of about 1.5 diopter each. This means we have a 1 diopter power. This produces a wide-angle effect to the supplemental images. There's clearly some distortion as a consequence. So how do we deal with this? Mercifully, we now have some very sophisticated software available that's capable of analyzing lens distortion and correcting for it. To help make that possible, we first provide the entire apparatus with a view of a metric by which to calibrate the system. This one happens to be a skeletal cube. Using such a metric, the software is capable of characterizing the lens and/or lens-mirror combinations, and with that task accomplished, other software solutions can be employed to extract the 3D data about the subject, from which may be constructed a 3D model of the subject in full motion. There are drawbacks, of course. One is that in spite of the use of front surface mirrors, we do incur some light losses. Consequently, to keep the exposure equal, we have to carry a 0.6 ND filter for the unobstructed portion of the image. So that's a 2-stop loss there. Then we have a focus differential between the unobstructed view and the reflected views. Obviously, we are extending the distance by the folding image beam twice. So this requires fudging the critical focus point so that it lands somewhere between the two, and then stopping down to extend the depth of focus to encompass both planes. So this technique requires a fast film stock and/or a lot of light. But given that the principal purpose here is the acquisition of the z-axis data for an image that will undergo considerable revision in the post-production process, this may not be too great a burden. In summary, then, we've shown at least another possible way to acquire imagery that will yield z-axis spatial data for application in motion picture and television visual effects.